Afternoon, everybody. My name is Mohammed Bajwa, and I'm a graduate student at University of Wisconsin in Madison. And the topic I'll be presenting today is the use of steel fibers in reinforced concrete coupling beams under wind simulated loading. So recently, there has been growing interest by the engineering community to investigate allowing inelastic deformations for components designed for wind loading. Similar to performance-based seismic design, but in case of wind design, the inelastic deformations are not as large as compared to the ground deformations, but the duration of cycles and the number of cycles is a thing of concern. So there was a need or a gap in the research to evaluate the behavior of some of the critical structural components under extreme wind events. So coupled wall systems are typically used in mid to high-rise buildings because of their superior lateral strength and stiffness. In this picture, you can see a core wall of a building where openings across the shear walls are connected by means of coupling beams, or commonly referred to as link beams. And in cases of non-seismic regions, these are designed as slender or deep beams using the ACI 318 provisions. So in a previous study done at UCLA using reinforced concrete coupling beams, there were shear stresses obtained as high as 7.5 square root of F prime C, and a rotational demand of 1 theta y was applied. So the purpose of and the motivation for this study was to evaluate SFRC coupling beams and applying higher shear stresses based on the superior shear strength provided by SFRC. So there are a variety of steel fibers that are available in market. Some have mechanical anchorages on the end, some do not. The one in the picture is the one that we used. It has double hooks on the end, and that provides additional anchorage in addition to the anchorage provided by the bond with the fiber and the concrete. So the steel fibers typically range in length of about 1.2 to 2.4 inches, and length to diameter ratio of 50 and 80, and the tensile strength of 160 to 330 KSI. And the maximum practical dosage is about 200 pounds per cubic yard, and after that workability becomes an issue. And these steel fibers, they come in lumps of individual fibers which are glued together, and once it's mixed with the concrete, they dissolve randomly throughout the concrete mix. So in a previous study done by my predecessors on coupling beams under large deformation cycles similar to seismic cycles. So in coupling beams which had aspect ratio between 2 and 3, they were able to eliminate diagonal bars and simplify the transverse reinforcement, which saves cost in terms of the steel, and also in terms of the cost of installation of these diagonal bars. So there is good potential of using SFRC and subjecting them to inelastic cycles. So again, this is a coupled wall system shown, and with a clear span length of Ln, and under the application of a load, it goes under a certain displacement, and that displacement divided by the clear length is what we define as the drift ratio. And as you notice, the end blocks, which are representing like the end regions of a wall, has some axial restraint, which is typical in a coupled wall system that undergoes deformations. So in this experimental study, we tested 4 coupling beams. All of them had an aspect ratio of 3.0 with a clear span length of 48 inches and a depth of 16 inches. The target shear stress we used was 15 square root F prime C for the first coupling beam, and the rest of them were 10 square root F prime C. The reason for using 15 square root f prime c was in some buildings in Chicago, we've seen that some steel coupling beams had that kind of a stress. So since we were using SFRC, so we wanted to try achieving higher stresses in coupling beam under wind simulated loading. And the specified concrete strength was about 8,000 psi, and the volume of fibers that were used was about 0.65 and 0.5% of the total concrete mix. So the coupling beams were designed based on with the ultimate shear stress of 10 or 15 square root of f prime c, and the contribution from SFRC was 5 square root of f prime c. This is based on some previous studies, and the transverse reinforcement was done with the Chapter 9 slender beam provisions. And additionally, we assumed about 5% of axial load in the design. And just for your review, we have one of the coupling beams, and the coupling beam was prefabricated, made with SFRC, and the longitudinal bars were number 9 throughout, and number 4 hoops were used. And the clear span was 48 inches, but we had additional 3/4 inches to embed into the end blocks. So this is the test setup that was used in our lab, and so for the sake of making the testing feasible, we rotated the coupling beam 90 degrees, and the bottom block was connected with the strong floor, and the top block was connected to a reaction wall by means of an actuator. On the side of the coupling beams, you can see 2 steel arms which were used to provide axial restraint throughout the testing, and were facilitated with pin connections to allow lateral movement. And additionally, we had 110 kip loading cells to monitor the compressive forces induced during the deformations. So this is the coupling beam specimen, one of the coupling beam specimens with some sensors installed on it. And in the middle, we have the precast SFRC coupling beam, and then we have these 2 end blocks, which have reinforcement similar to what you would have in a shear wall. So as I mentioned, that there hasn't been much testing done on wind loading in the past. So this wind loading protocol was developed by some people at MK. We got this loading protocol from Mr. John Hooper at MK, and this is based on some wind loading testing at a site in Miami with a windstorm of a mean recurrent MRI of, I think, 3,000 years. So in this loading protocol, we have small amplitude cycles with a large volume, and as the storm or the ramps up, or the number of or the amplitude ramps up, we have smaller number of cycles up to 0.75 my. So my is the nominal yield moment that we used, and then we have displacement control cycles, which were 1.2 theta y and 1.5 theta y. And this would conclude the ramp up portion of the storm, and then you would have the symmetrical ramping where the cycles were induced in the reverse order. And here is just a graphical illustration of the wind loading protocol over time. Again, the cycles below yielding were force control, and above yielding were displacement control. So I'll talk a little bit about the results. So in the first coupling beam specimen, we saw shear stresses as high as 13.6 square root of f prime c, with a maximum load of about 140 kips at a drift of about 2%. And in the second specimen, we had shear stresses up to 10.7 square root of f prime c, with a maximum load of about 120 kips and a drift of 1.75. And in specimen 3, maximum shear stress of 9.5 square root of f prime c, and the maximum load of 100 kips at about 1% drift. And in the specimen 4, which had the lowest ratio of fibers, we saw shear stresses of about 8.2 square root of f prime c and maximum load of about 88 kips at a drift of about 1%. So overall, cracking and the damage that we saw in the beams was similar in all of them and would be considered minimal or negligible. Within the h distance from the interfaces, we measured crack widths, the flexural ones and the diagonal ones at the end of the wind loading protocol. So at the end of the wind loading protocol, the maximum flexural crack widths were about 1 millimeter or 1 by 24 inches, while the diagonal crack or shear cracks were about 1 by 64 inches and about 0.4 millimeter. There was some minor spalling at the bottom interface, but it wasn't considerable. It was the pieces that spalled off were about 3 millimeter in thickness, and there was a little bit of sign of concrete crushing along the beam interfaces. But other than that, there was no major damage. And in addition to some longitudinal yielding, we had no yielding in the transverse reinforcement. So I'll talk about a little bit about the drift components. So there are four sources of deformations that contributed to the total drift. So the first one is the deformations due to the yielding of the longitudinal bars. So as the beam goes under deformation cycles, the longitudinal bars extend over time. The second type of deformation is the flexural deformation of the beam itself, and then the shear distortions throughout the beam, and finally we had some sliding across the interfaces of the beam and the wall. So these are some of the results represent the contribution of each individual drift component at the peak ductility cycle, which was of 1.5 theta y. In all of the specimens, we had about 30 to 40% deformation, which was due to the bar slip or yielding of the bars. And due to the beam flexure and beam shear, they were similar across all the specimens, ranging between 25 to 30%, and sliding was about 10% across all the coupling beam specimens. So we estimated the normalized stiffnesses at each loading stage, which is basically the average of each cycle at each individual loading stage. And as you would expect, there was a continual loss of stiffness as you would ramp up and ramp down throughout the loading stage. One thing we did notice that the cracks continue to propagate during the ramp down phase, but there were no new cracks were formed during the ramp down phase. And the stiffness at the peak ductility cycles ranged from 0.1 to 0.13. As I mentioned, we provided some axial restraint, and in the design we assumed about 5% of the gross section capacity to be the axial force, and in all the coupling beams, the axial force we saw was at 5% or below 5%. So in concluding remarks, we saw that with the standard detailing and using SFRC, we can achieve shear stresses as high as 14 square root of f prime c with very limited damage. The peak ductility demand of 1.5 theta y. As a result of that, we had only longitudinal reinforcement yielding, but no yielding in the transverse reinforcement. And the total contribution to the drift from flexural deformations was about 60 to 70%, and the rest of the deformations were due to shear. And there was a continual loss of stiffness throughout the loading protocol. Finally, I would like to acknowledge the sponsor for this project, Baker Corporation, and I would like to thank my advisor, Professor Para, for his time and his efforts, and the staff at the University of Wisconsin and the Sandy and June Lee lab. Thank you very much.